Log on, tune in, find out. Another good idea from Cambridge.
Let me begin by thanking the organisers for also so kindly inviting me. It's nice to come back to one's original home university, and it's been quite fun. I have to say that the gremlin struck my own laptop. It decided to change all the fonts just 5 minutes before the start when I was trying to test it out. So this is what I've managed to cobble together on the Institute machine. So apologies if it looks a bit sort of rough around the edges. I should also say that though the talk, the original title and abstract that you received is...
1 minute, you need the microphone.
We want to record for posterity. We want Steve's comments. Yeah. That's the subtext. Steve's heartbeat.
Is that all right? Is that better? So though the original talk title and abstract, though I'm staying within that general framework, I did make quite a number of changes. So the title that you see here is what I'm really going to be actually talking about, which is Screening for Important Inputs by Bootstrapping. And here's a talk overview. The main message are in the first 2 points. What I want to do is to emphasize the value of bootstrapping. And from that point of view, I can perhaps modify Jack's question to the audience by sort of saying, how many of you have actually used the bootstrap in your own work? So quite a number. Okay, very good. Okay, so perhaps I might be preaching to the converted here, but nevertheless, this talk is, I have to admit, it's really just a big plug for bootstrapping. So if you haven't used it, then hopefully I'll persuade you through this talk to at least consider it more seriously. The other point is that bootstrapping is very amenable to parallel computation, so it's something which should be able to sort of take advantage of recent advances in computing hardware, even at the laptop level. What I'm going to do is not to give a broad review of bootstrapping, but what I'm going to do is to just focus on just one single, very simple example, which hopefully you will all be very familiar with, so I don't have to discuss that aspect of it, and then that means I can just focus on the bootstrapping aspect. And the screening for important factors in a linear model is what I'm going to actually talk about. I have to emphasize, however, that bootstrapping can be used really in a very wide variety of contexts. It's particularly useful in non-standard sort of problems, like, for example, generating critical values in difficult distributions like the now distribution of Anderson-Darling. The Anderson-Darling, hopefully you'll be familiar with, is probably one of the best goodness of fit tests around. It's not as widely used as it ought, mainly because it's so context dependent. The actual form of the distribution you're looking at, whether you're estimating parameters, all change the null distribution, which means you have to have different tables for different situations, and that's, I think, really hamstrung its much more widespread use. But with bootstrapping, you can basically just generate your own critical values on the fly for whatever problem you actually wanting to apply it to. The other aspect, and this is the one which I'm actually going to be focusing on, is that I think that sometimes bootstrapping can give really quite nice fresh insight into what are really well-known problems, and the screening example is what I'm going to illustrate this point actually with. I should perhaps just get over the parallel implementation side. I'm afraid I was far too optimistic when I put this into the original talk title and abstract. At that stage I was thinking of changing my laptop, and and I've still not done it, because what I wanted to do was to buy one which actually enables one to use one of these API open software which is now available for the latest generation of graphics processing units, such as the NVIDIA GPU. It's all in a CUDA, a Computer Unified Device Architecture, and what it does is make the stream processors of such a GPU accessible to parallel computing applications. Is anyone here actually very familiar with this kind of technology or use it? Does anyone use it? Oh, good, right. So in fact, those are people I can sort of come and talk to, because I need perhaps some advice on how to, on which laptop I should be perhaps considering for this. I noted, in fact, that in the latest issue of Tomax, Park and Paul Fishwick have actually got a very nice article using exactly this sort of technology for a queuing network analysis. So let me just go straight on to bootstrapping and then focus on the particular example. Fortunately, Jack has already sort of covered most of this, so I can go through this very quickly. A large number of statistical problems boil down to this little schematic here. We have some distribution from which we've obtained a sample y, and from that we calculate a quantity of interest. So this could be perhaps an actual real experiment, but in our case I should really be perhaps sort of emphasizing that this could very well have sort of come from some large simulation study. So the point here to emphasize is that this could be actually quite expensive to obtain this sample. The calculation of the test statistic could also be quite sort of complex as well. But at the end of the day, that's what has happened, and the only question really one can ask of any random variable is what is its distribution? And really, bootstrapping answers this, I think, in a very nice way by applying the fundamental theorem of sampling, the Glivenko-Cantelli lemma, twice. The Glivenko-Cantelli lemma is just simply saying that the empirical distribution function of the sample will, as the sample size tends to infinity, tend to the distribution function that the sample came from with probability 1. So that really is the basis of all statistics. Really, without it, we really wouldn't be able to do anything meaningful at all. So there's the question, and the bootstrap answer, how does it deal with it? Well, it just simply says, well, if what we would like to be able to do is to repeat the sampling situation, but in a much simplified way. So why don't we just take the EDF of y, apply the fundamental theorem to say that for a large enough sample, this will then represent this well, generate a set of bootstrap samples in exactly the same way as we got the y here, calculate then for each of these samples, because each of these looks just like the y, the corresponding statistic of interest. And lo and behold, here we've got a sample of the statistic of interest. So why don't we use the Glivenko-Cantelli lemma again and look at the EDF of that, which would then answer the question. So really as simple as that, and that's all there is really to bootstrapping. And it works really well. So in the application I'm going to talk about, it's to a linear model, standard one, set out in the usual way. Your response that we're looking at is a linear combination of a number of p independent factors or variables, and the coefficients associated with these factors are unknown. There's also a unknown constant there, and also the error that we've added in here is got perhaps a normal structure with variance sigma squared. And we would typically estimate these unknown quantities by, say, maximum likelihood. Now, if we're not sure which factors are important, then we've got 2 to the p plus 1 possible models. If, say, we've got a problem where each of the x's is at sort of 2 sorry, not at each level. If, depending on whether we keep a factor in the problem or not. So if we denote a model by the number of factors, by the factors that we keep in the model, there may be, say, little p factors. This is really just a subset of the full choice of capital P factors that we have. We've got 2 to the p plus 1 possible models of this form. What I'll do is I'll denote the full model by capital M and little m for any little sort of submodel. Well, this problem has been discussed at length, especially sequential backward-forward selection and variants of this to try and deal with non-orthogonally designed situations to avoid selecting a final submodel which doesn't include all factors which might be deemed important. There are more sophisticated Bayesian strategies which I think actually are for me, a rather sort of more comprehensive and better approach. But I won't be considering this. Instead, what I'll do is I'll consider the bootstrap approach to this problem instead. And 3 issues that we need to perhaps bear in mind or handle, deal with. There's the issue of the criterion measure, what we're going to use for deciding which actually is going to be considered to be the best model. And we need also to know if, once we've selected the model and we fitted it to the data, whether it's actually a sufficiently good fit as well. And finally, we would want to know if this best model is a clear winner in the sense that there may be competitive alternatives which might be really sort of quite close to this supposed best model. And in fact, we'll see in the example and in examples that I'll show hopefully with time at the end, that this is really quite a sort of big issue. I'm thinking mainly of perhaps the more sort of general sort of OR and social sciences uses of the linear model, where this is very popular, and in data mining type situations where you find that there are a very large number of factors, and really there actually are a very large number of competing alternative models, which I think some of the certainly the more classical technology like these stepwise methods don't really, I think, fully sort of reveal the actual sort of situation that we're actually in. Well, the first of those issues is the criterion measure, and the one I'm actually going to use is the CP statistic proposed by Mallows. How many here know of the Mallows statistic? All right, very good, a good number. Mallows actually won a prize for it, and I think quite rightly so, and I think in fact in a lot of textbooks on screening the Mallows statistics, and it perhaps deserves more prominence. It's basically a combined measure of the bias and the variance, and is very easily calculated. It's related to the Akaike information criterion, in fact asymptotically. They both are essentially the same. One thing that Mallows showed was that if you actually choose a submodel with p factors and it's satisfactory once fitted to the data, that in the sense that it has no bias, then the CP value will be actually quite close to p. And you would expect a selected best model should really have a CP less than the number of factors selected. So a simple selection criterion, therefore, is this min CP one, where if you were able to list all the possible models and fit each of them to the data set, calculate a CP value for all of them, then you could just simply choose the one with the smallest CP value. And if it satisfies this condition, then you've got a reasonable model. The following is perhaps more parsimonious, which is to say, well, this is okay, but I would like to make sure that the model selected has the smallest p possible, subject to satisfying this CP less than p condition. So why didn't we find the smallest p naught, where there is a submodel satisfying the condition, and then amongst all the models where p is actually equal to p naught, find the one where the CP is the actual sort of minimum. I've called this the unbiased minimum p method for obvious reasons. And perhaps we should have a look immediately at a data set. This is one which I will actually do the analysis for this at the end. It's actually fire and rescue, and it is actually a simulation example. It was actually an MSc student who went to work for the Ministry of Defence, and she was looking at fire and rescue service, and she actually developed a simulation model. And in fact, in this one, the full model had something like well, she reduced it down to 20 what she thought were potentially important factors. So in this case, the total number of submodels is over 1 million things. Now, I've not got all each of these points here represents one of these submodels fitted to the data set that she obtained from her simulation model. And the plot is of the CP value for that fitted model against the number of factors that actually are used in that model. There's actually only around about a couple of hundred points there, perhaps more, slightly more than that. Certainly nowhere near the full 1 million there. A good choice would choose one of the models corresponding to the point below this line. The minimum CP value is obviously one of the ones here, from this set anyway, and the unbiased min P1 is the one where we actually go for the smallest p, where there are models which go below with points below the line, and the minimum CP1 is that point there. Okay, so that's a nice, simple explanation of what those two criteria are actually doing. What Mallows actually did in a follow-up paper was to look at the situation where a large number of the factors had coefficient values uniformly distributed near 0 with density lambda, and he was able to show that the scatter plot, if you actually did the full thing, he was able to characterize the lower boundary of this to being the cubic there that I've got up here. And also, that means we can actually work out the intersection of the of that cubic with the CP equals P line. And if this picture that I've just sort of shown is sort of typical, this suggests that perhaps we don't really need to examine all the possible submodels, but just have a representative set. And providing there's some good ones which actually characterize this lower boundary, then that's all that's needed in order to be able to allow us to select a good model from that, what I would call promising set of submodels, and deal with the best subset selection problem in that way. So that's the basic approach then, is to select a set of promising models using bootstrap resampling. Well, here's the bootstrap analysis, and in fact, courtesy of Jack, he's covered all this. I'm actually going to use parametric bootstrap sampling. Basically, what we do is we take the fitted coefficients from the original data set and use that to recreate the regression function part of the formula, and essentially generate bootstrap samples by just plugging in our own generated errors coming from the normal distribution with the estimated sigma squared. And in fact, in answer perhaps to Shane's question about what to do with uncertainty, well, I think in resampling is actually a very easy answer to it, is that we, and in fact, my analysis here, in fact, is actually falling into the trap that you pointed out of just assuming that the B hat here is a good one-off representation of the unknown true B. But in resampling, it would be easy to perhaps repeat this, where we actually resample this as well from the distribution of B hat, and that would give us some idea of the actual inherent variability in the process that I'm actually describing. Well, for each of the bootstrap samples, what we can do then is we can do exactly what we want to do with the original sample. We can fit the full model to each of the samples, and what I'm going to do here, in fact, is for each of these bootstrap samples, I'm going to generate just a single promising model. And I'll do this by looking at the t-values of the fitted coefficients. I'll explain what these are in a moment. And just choose those coefficients with large t-values to keep in the actual submodel. And that will be the actual selected promising model. There'll be a maximum B of these, but of course when I'm actually choosing these submodels, some of them may actually be the same for different bootstrap samples. So in fact we'll actually have probably rather fewer than the full B, but whatever we get will be the full set of promising submodels. The t-values are really just simply the standardized coefficient estimate values, and we know that student t distribution when the b is actually 0. So the t's basically provide a simple criterion for deciding whether b is important or not, and choosing ones with large t is a very natural thing to do. In fact, if the model is actually orthogonal, this one model per bootstrap sample is actually rather more direct in what it's doing. If we set the critical level for t to be root 3, in fact, it's actually equivalent to the unbiased min-p selection method. So we're actually not having to do any of this sort of hunting around. Back to the picture, we would actually be immediately identifying that model straight away without any worry about the need for promising sets or anything like that. And in fact, if I can perhaps just keep that on for a moment, if we actually look at the criterion there for the orthogonal case, if we set the a equal to not root 3 but root 2, we actually got the min p there. So the methodology is actually very straightforward in the orthogonal case. Then to finish the thing off, what we can do is we can actually use the unbiased min-p method to select from the set of promising models now. So this is the non-orthogonal case, the best model for the original data set. And the nice thing is that we can do exactly the same thing for each of the bootstrap samples as well. We actually look at the promising models for each of the bootstrap sample, and we actually choose the best one for each of those as well. And the point of that is that it allows us to see how reliable the best model for the original data set is. If it keeps on appearing when we do this for all the bootstrap samples, we know we've got a very reliable model. If, however, as we'll see in the example, we actually get a whole range of different best models, we'll see how it's a very simple assessment of the quality of the solution that we've actually sort of obtained. Let me just jump, as time's really running out quite quickly, with this numeric example. This is in fact actually from the StatLib library. It's actually not a simulation example. I'll, if I have time, show you a simulation example. It's actually a body fat example. It's an observation of 252 individuals, and we're actually looking at percentage body fat. I'm actually getting to the stage where I'm starting to worry about my weight. So this is actually I thought it was a rather nice example. And in fact, it's here are the 14 possible explanatory factors. Most of them are just measures of neck, chest, abdomen, hip, thigh, knee, ankle, biceps, forearm, wrist circumferences. So you might want to sort of try and look at the data and see whether you might be considered to be fat or not in this. Perhaps this is a rather interesting one, the body density. This is actually an Archimedean measure of body density where you immerse the subject underwater. Not quite right, of course, because unless you're proposing to drown your subjects, you don't have water in their lungs. but that's the actual sort of set, the data set. And for this one, there are actually 2 to the 15 models, minus 1 if we don't fit the null model. So there's actually over 32,000 of these. If I use this bootstrap method with 500 bootstrap samples, it actually identified 236 promising models, and these are the ones actually shown here. And you can see, and what I've also done is I've actually worked out the full set of CP values for all 32,000 models offline, so to speak. And I've not displayed them all, but I've shown the lower boundary corresponding to the full set. And there it is. And you see that of the 236, we have actually identified all the minimum CP values right around the range where we're actually mainly interested. So I think this has worked really perfectly well in this particular example. Some quick other ones. This is the fire rescue orthogonal simulation done exactly in the same way. There are actually 20 factors here, so there are actually over 1 million actual submodels, which I have actually bludgeoned my way through and got the actual underlying curve. With only 500 bootstrap samples, in fact, you haven't quite got it right. If you actually look at these, it's actually missed 1 or 2 over here. But over this main range where the critical crossing line takes place, it's actually picked out all the minimum models there. So it's really sort of done quite sort of nicely. Other examples which I perhaps won't sort of go into. What I'll do instead is to perhaps finish by, I think I've probably just about enough time to do this, with an actual demonstration of how the calculation is actually done. And it's all on a spreadsheet. So if you're interested in this and would like to see the have access to the spreadsheet, I'm quite happy to send it to you. Here's the body fat example with the sort of data, and the spreadsheet has a number of sheets attached to it. There's an analysis of variance sheet where if you oh gosh, how do I activate
right
the
upwards is enable content, just there on that kind of goldish bar, right in the middle, right there.
Oh, right. That's it. Great, thanks. So there's the analysis of variance done for this, and it actually gives you the dispersion sort of matrix at the sort of bottom, showing the level of correlation between the various parameter estimates. So it's clearly a non-orthogonal example, obviously, as the data is based on patients. And here's the bootstrapping, and what it's doing here is to actually generate, in fact, rather quickly, the 200 bootstrap samples. And it's actually carried out the actual estimation there. And I've got here on the left-hand side here the set of distinct promising models relisted, but in order of how often they came up as being the best fit to their data sample. And this is the point of this, is because what we're essentially doing is repeating the original experiment and seeing which model actually comes out best. And we can see that there's actually a huge range of variation with no clear sort of winner, with really quite a sort of range of actual models coming out. There's the actual analysis which it actually carries out of the actual, oh dear, the data set. And the thing that I like to do is shown at the sort of bottom here, which if I can change, I'm not sure whether I can, yes, I can change the view size. Should something a bit smaller. Let's make it really small. If I click on this button there, what it's doing is I've actually listed the best fits that we obtained from the bootstrapping, and I'm just colouring in those factors which were actually selected in the submodel. I'm not quite sure why it's sort of paused, but you can see at a sort of glance which of the factors are actually coming up in a consistent way in this set of bootstrapped best models. You have to be a little bit careful here because you need to sort of take into account the actual frequency of occurrence. So the top one did actually come up, I think, something like sort of 9 times. But nevertheless, it's pretty clear, I think, from this really, basically the variety of variation possible in the best fitted model. But it's also clear also that for example, density, the weight and the height, and no surprise, the chest, abdomen, hip, and rather strangely, the forearm are actually quite important measures of predictors of the percentage body fat in a person. Okay, so that basically finishes. If I don't know whether I'll be allowed to just. Well, in fact, I can just summarize it without showing the slide. 2 things really fairly obvious. One is that. Oh, right. 2 things fairly sort of obvious. One is that if you're interested in this kind of spreadsheet package. I've actually got any number for different examples, including the Anderson-Darling one. This is just for this particular application. And if you're at all interested, I'm quite happy to send you appropriate spreadsheets or copies. In terms of further work here, obviously the parallelization of this, clearly with all these independent replications, doing this in parallel would greatly speed the thing up. Though, as you can see for this example, it already runs pretty fast. All the resampling really takes next to no time anyway. And perhaps one final comment, that I think bootstrapping might be actually a very good way of tackling this problem about input parameter uncertainty. You can you can use it in the Bayesian context as well. If you have Bayesians or prior information, you can do a full Bayesian, including analysis of the posterior, using resampling type methods. So I personally, in a lot of situations, would probably lean towards considering, say, importance sampling rather than Markov chain Monte Carlo, simply because the Markov chain, you require sort of burn-in periods, things like that, whereas if you've got the importance sampling set up right, you're doing independent replications, and again, you could hit that with a parallel computing setup. Okay, so
I think it's any questions we have? Yes, Jack.
Russell, I assume that you can extend your bootstrap approach to also investigate not only what's the important subset of first order effects, but also look at second order effects, maybe logarithmic transformation.
Yes. But I mean, the nice thing about this is I was able to use the mallow statistic in a very sort of nice way. And I suppose you would still deal with the interactions. Yes, you could do. Yes.
I guess we have some coffee. Okay, thank our speakers, all three of them.